More on test design. Combinations testing. It's very hard for me to imagine a real software testing project which didn't involve multiple variables interacting with each other, influencing the behavior of the software under test. It's very rare where you only have one variable or a very small number of variables that are independent. They usually work together, churn against each other, and basically try hard to do everything in their power to get the application to do something different than what the intention of both the customer and the developers are. So combinations test design is a series of techniques of test design which can be used when you have multiple variables and multiple conditions. And there's basically two approaches that I'm going to talk about broadly. One is based on knowledge of the type of transactions people are going to be using, and the other one is based on some combinatorics and a little bit of what might be called the discrete math of orthogonal arrays. Combinations testing. So it starts off with Vilfredo Pareto. So Vilfredo Pareto was an Italian economist who studied in the late 1800s and early 1900s the distribution of wealth. And Vilfredo Pareto discovered that the wealth distribution was a little bit lopsided. In fact, he found out that 80% of the wealth is in the hands of 20% of the population, 80% of the money, 20% of the people. This was a distribution that he noticed and observed to be true. It sort of makes sense, actually. Today, people talk about even worse ratios than that, like 90% of the money is in the hands of 10% of the people. It's things like that you hear about. Anyhow, the 80-20 rule started with Vilfredo Pareto, an economist, and he was keeping it in the world of economic theory. It wasn't until Joseph Juran came around and published his Quality Control Handbook in 1950 that he was able to apply the thinking of Pareto to the world of engineering. Now, this was way before software engineering. I have to say, 1950, there was a lot of quality systems, a lot of engineering systems, but it was mostly process modeling and production that Joseph Juran was looking at that time. But Joseph Juran looked and studied and understood a lot about quality. And he basically took Pareto's work and applied it to engineering. And he found that in general, in many situations that he was running into in production, that there was always a small percentage of the population accounting for most of what he was observing. So this became known as the 20%, 80-20 rule, which goes like this: 20% of a studied population accounts for 80% of the measure under consideration, or to put it in very simple terms, there is always a vital few and a trivial many. And what are they? And if we know them, then we can focus our experiments on the vital few, get the thing optimized and working for that, and we'll be in good shape economically and from an engineering perspective. So Pareto combinations testing, something that we can do if we have some knowledge of the transaction history. How will the users behave? How have they behaved in the past? Is there a pattern? So the first thing is to start with a transaction history, literally a log file that has each and every transaction, when it took place, so that we can count them up over a period of time. So we can count how many of this type of transaction happened in the last 6 months, how many of that type of transaction happened in the last 6 months, and we can actually count them. And once we can count all these transactions, we can then make a list of them and draw that as a histogram, sort it by decreasing frequency, and we can then see if we have a Pareto distribution, which is going to become evident from the diagram. And once we've got that diagram, we can basically find the sweet spot. What is the sweet spot where we have 20% of the transaction types that take place 80% of the time? And that sweet spot is where we would focus our testing. This is also very, very handy if you're doing automated regression testing and you don't have a lot of time and budget to test everything. Well, start with the Pareto sweet spot. Get those transactions tested and then work out from there. This is an excellent starting point. And the bugs that you find when you run tests of the Pareto sweet spot are almost always bugs that matter to users because they're infrequently used transactions. This is what a natural Pareto distribution looks like. You'll see it's a decaying curve. It's going a nice distinguished pattern like that. And when this curve is evident, it's pretty clear you've got a Pareto distribution. And if you look at the bottom here, in this case, we have 241 different transaction types, and the most frequent ones are really way up here. And literally that's like between 1 and 45 or 49, where you have pretty much 20% of the transaction types happen 80% of the time. If you do the integration of that, I think you'll find it's a pretty close estimate. So this is a natural Pareto distribution. Find the sweet spot. Focus your testing on the transaction types in the sweet spot. And that's all of the conditions, all the transaction types and everything. So that Pareto analysis helps you out. And it's really useful if you have a transaction history, if you don't have much time, and if you want a warm and fuzzy feeling in your tummy that normal things work normally for normal people. If, however, you are concerned with outliers, you are concerned with bugs that aren't something that happens when normal typical transactions go on, but when unusual sequence of events happen, or when strange combinations happen, which can happen, and when they do, if they lead to dramatic cataclysmic events, we are in deep trouble. So sometimes we want to build confidence that variables interact with other variables in a healthy manner. And to do that, we really move into a different type of combinations test design, which uses basically a little bit of math to help guide us. I'm going to start here with pairwise combinations, but you can look at this as the pairwise can also be triples or quadruples or n-tuples. And n can start as low as 1 and as high as you go, as high as the number of variables. So we'll start with pairwise, and you get the gist of this here. The pairwise is something that's been used in software testing now for over 20 years. In fact, it was invented in domains other than software testing in something called design by experiments. Some people would call it orthogonal arrays testing, Taguchi methods or like. And some of the basic math of it goes back to building magical squares by, actually in medieval times, by monks who are spending their lives doing all sorts of weird analysis here. So it's not a new type of math, but it's a cool thing to do. First, what do? You start, okay, I have multiple variables. I want to start and identify the variables of interest, the variables that I want to study their behavior interacting with each other. So those are dependent variables of interest. When I say dependent, the behavior of the application depends on the values of these variables. And so I try to get a list. Now, I'd like to get as small and reasonable a list as I can, but sometimes that still gets up to 10 or 15 variables. So it's sometimes quite significant. For each variable, I want to identify the values of concern. If you're following the test design stuff in order, the type of value ranges of interest might be almost the same as equivalence classes. So you might say, okay, for each variable, what are the valid equivalence classes? I want to identify the valid equivalence classes for each variable. And then for each pair of variables, what I want to do is I want to find at least one test case which exercises all the possible values of that pair. And I want to build a set that has that truth for every pairing of variables. The notion of dependent variables is important. Think about a clothes washer or a clothes dryer. The water level, temperature, wash cycle probably influence the washing behavior and the washing logic of it, but the color of the appliance probably does not. Or in the dryer, the speed settings and the heat settings, the thermal temperatures probably influence the drying logic that you want to test. However, the light being on or off probably doesn't make too much of a difference. So you want to focus on what you believe to be the dependent variables. To do pairwise combinations analysis by hand is tedious. Some people say it's worth learning how to do. If you do want to see how to do this by hand, there's a chapter in the book by Lee Copeland, A Practitioner's Guide to Test Design, that will walk you through it. I, however, prefer to use tools that are calibrated to help with this type of test design. And the tools that I like to use are all pairs or PICT. Usually these days I use PICT. PICT is a free tool put together by Microsoft to help people do complex combinations design. And it is really, really flexible and lets you define almost any combination of variables, and it'll give you a really, really beautiful set of test cases. Now, the thing is that it sounds to me like pairwise testing might generate large test cases, but actually, if you're clever about this, it generates very reasonable sized test cases given the problem space. Let's imagine we're going to test the Rapomatic. Remember the variable identification for Rapomatic, how many variables there were that related to the wrapping logic? Well, if I wanted to do some serious testing of the wrappability of the Rapomatic, and I knew that the wrappability of the Rapomatic depended on the chocolate type and the configuration of the chocolate and the paper type and the ribbon type and the speed of the conveyors and the type of the box and the viscosity of the chocolates and the size of the box and the weight of the chocolates and the size of the chocolates. All of these factors influence the wrappability, and I want to test them in combinations with each other. I mean, I want to vary the chocolates with the paper. I want to vary the ribbon with the weight. I want to vary the box size with the chocolate types. I want to vary any pairing of those variables against each other and see how does the Rapomatic behave. So it's a question of basically, for me, starting here, what is a reasonable set of pairwise combinations for this? I choose to use a tool called PICT. And by the way, if you do the math here, if you look at how many combinations there are, there's way over 1 million possible combinations if you were to test them all, which would be a rather long, but perhaps a fun testing project, but a very long one. And if you take a look at the result of using the tool PICT here, this, by the way, is what the input of the tool PICT looks like. It's just a text file. So the output is a spreadsheet, and each row in the spreadsheet is a test case, and each column is a variable type. So chocolate, configuration, paper, ribbon, conveyor speed, box type, viscosity, box size, weight, and size. Those are all the variables. And then you'll see the tests going down here. And we have what is called a pairwise complete set. So we have every chocolate with every configuration at least once. Every chocolate with every paper type at least once. Every chocolate with every ribbon at least once. Dot, dot, dot. Every chocolate with every size at least once. Plus, over and above that, every config with every paper at least once. Every config with every ribbon at least once. Dot, dot, dot. Every config with every size at least once. Dot, dot, dot. All the way to every weight with every size at least once. Take any two variable, every combination of them at least once. And that gives us a total of 51 test cases using the tool PICT. This is not necessarily the minimum set, but it is quite a reasonable small set, and it's minimal. In my experience, it's within about 1 or 2 of the absolute minimum. If you want to prove mathematically what's the minimum number, the PICT tool is practical, and it's very practical for someone to run 51 test cases to test the wrappability of the Rapomatic, as opposed to well over 1 million test cases. So this is basically how it's done. You take the variables, put them in a text file here, the variables chocolate type configuration, followed by a comma separated list of the values, ram it through the tool PICT, and presto, you get a spreadsheet with all of the interesting test cases to try. Now the Rapomatic, of course, if we tried all those test cases, it would be, you'd uncover problems between variables that interact with each other. The assumption here is that we're not going to try all the triples or all the quadruples, but we're going to try all the pairings. And it works out that in software engineering, that usually gives you a fairly thorough and a reasonably high quality system. Now I've got a case study that I'm going to share with you in class for a combinations case study that I did, where we used this type of analysis, and a company that was totally saturated with bugs, which were what we called co-resident application failure bugs on systems using antivirus, anti-spyware, parental control software. All of that stuff was yielding tons and tons of bugs. We did this type of pairwise analysis, identified about 40 test configurations, and then tested very thoroughly on those configurations, every major release, continuing the process. We were able to basically almost completely eliminate that class of failure. Now, we didn't get rid of all the failures of everything, but the type we were looking for, the interaction between things at the system environment level, we basically eliminated because we found them in our labs before we deployed the software into the field. So there's a very comprehensive case study showing the value that it's an incredibly beneficial approach, and it saved that company a fortune in support costs. Now, it's possible that you have a little more complex of a problem. We call these constrained problems. Remember the wrapping rules. When I talked about decision tables, I said we had wrapping rules around the Wrap-O-Matic, and we weren't allowed to put wire on hollow chocolates because we'd crush them. And we weren't allowed to put ribbons directly on chocolates without paper in between. Well, tools like PICT allow you to define your test combinations problem with constraints. So this is an example of a pairwise complete testing problem described with constraints. Now, the tool PICT comes with a help system that describes the logic and the syntax used for defining the constraints. It looks a little bit like the C programming language. Don't blame me for the syntax of this. But basically, you start off your file with a list of the variables with the options you want to combine. So you have all the variables and the options you want to combine. And then you follow that by statements of the constraints. And there's basically if statements of all sorts. In this case, what we're saying is, and remember, in the description of the help for a tool like PICT, there's tons and tons and tons of different ways you can represent the constraints, right? There's a lot of syntaxes for that. In this case, I just chose this one. So if ribbon is in the list wire, then viscosity must be in the list solid, jelly, semi-solid. So if ribbon is wire, then the viscosity cannot be hollow. Similarly, if there's no ribbon, there's no paper. So if paper is none, then ribbon is none. So if paper is none, then ribbon is none. Now we run this through the tool PICT, and it generates for us a set of test cases. And in this case, they follow the constraints. So if you look at paper none, ribbon none, so paper ribbon, it's always none none. So if you look at none here, none none. If you look down, whenever there's a none here, there's a none there. None none, and the other none none. If there's no paper, there can't be a ribbon. None none. So you'll see that this is a list now. It's 55 test cases, but it's got a reasonably small number of test cases. You're comparing to 1 million possibilities here, and it does not violate the constraints. So all of these do not violate the constraints. These are all tests that should succeed. You can have multiple constraints and combinations of them. This is from a real project I worked on where they were testing a lab full of routers. And they could basically have a single or multiple sets of routers, and there could be between 1 and 5 of them. And each one of the 5 had 5 parameters, which could be in 3 states, on, off, or none. So that's basically the configuration parameters for their router test lab. And then we defined all these constraints. So depending on how many RCs are there, certain values are constrained for the other options. So we put all that in there. And then when we ran that through, it came out with basically 25 test configurations. And this company was worried that they would have to set up literally hundreds and hundreds of test configurations to test the router. But with this approach, they ended up with 26 configurations, which they were easily able to set up in their lab environments and exercise the product quite thoroughly before every major release. So this is constrained pairwise combinations testing. Now, just to suggest a couple of things here. First of all, it is also possible that we want all ones. So sometimes we don't want the variables to interact with each other, but we want each one to appear at least once. So we can do an all one set, tool like PICT to let you do that. You can also do all triples, quadruples, and tuples up to the number of variables in your list. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, there's 10 here. So you can try to do all 10s if you want. That would be a horrific, that's the multiple million case. But the tool lets you do it. The tool also lets you do for some variables ones, for some variables pairs, for some variables triples, etc. Although on commercial projects, I have never had to do more than pairwise, and I've seen all sorts of technologies over all the years, and I've done great work with this. I do know that if you want to increase your confidence, you would go up to triples on the sets of variables that you're worried have three-way interactions. And there are certainly bugs that are triggered with three-way interactions, although my experience is the ones I want to ferret out are the two-way ones, which can also show up in three-way interactions as well. When you find problems with pairwise combinations testing, sometimes they're very difficult to report or describe to people because it sounds like a weird permutation or collection of parameters that may never happen in the real world. And the answer is that's true. These are not necessarily realistic tests. These are tests that are great at ferreting out bugs, but they're not realistic. So you got to be very cautious because some stakeholders will say, why are you testing that? You are testing something that is not realistic. But you've got to mention that each test is adding pairings, and the pairings are all possible, and the pairings are all realistic. And even though no customer may ever order this, by doing this test, we're exposing bugs that can happen in all sorts of realistic scenarios. So it does take a teeny bit of test advocacy sometimes for the combinatorics testing. So anyhow, I urge you to learn a tool like Pict. There's a copy of it I've put in the my courses Dropbox area, and it should be quite straightforward to install. Although the version that I have is only supported on Windows. It's from Microsoft, and so Windows is their platform of choice. I do suggest that if you want an online version, you might go to www.amibugshare.com, which is basically an online version of Pict, where you could submit the input file and download the output file. I believe the output file in that case is going to be in a CSV, comma separated variable format. So that's it. Thank you very much. Until next time.